Hi, this is time for having a home exercise and practice for board exercise. So the first one as a home exercise to figure out the resistance to inspiration. So for this, we can consider a simple ventilation model as a big jar model as a whole alveolar space. So we can have this, let's say, ventilation as a jar model, so which is like this. And then we can consider our alveolar space as this big jar. Then the driving force for all this airflow is a pressure difference. So we can define this point as a pressure of atmospheric pressure. And then the pressure inside here is a pressure of alveolar space, ALV. And during the inspiration, the flow gets inside, rushed inside. So that volume flow rate, V dot, upper dot, is, we know that from the equation we learned, it's driving force, which is pressure difference divided by resistance R. So the given delta P between the atmospheric pressure to alveolar space, which is -5. So that difference is 5 millimilli Hg. And we have calculated our volume flow rate, such as, for example, like 12 liters per minute. Then the resistance can be calculated as pressure difference divided by volume flow rate, which is a 0.4 millimilli Hg multiplied by minute per liter. So now let's move on to this board exercise, which is alveolar ventilation rate and partial pressure of oxygen. For this, we will again define our system and system boundary using this alveolar jar model. So let's see. First of all, it's important to make a system and also the dead space. So this is the airway and this is a whole alveolar space. So let's define an open system with this blue dotted curve. So this is our system. Then there comes an exchange of volume of flow rate during this inhalation and exhalation. So when there is an inhale, then like this, there's a volume flow rate of this. And all this driving force as a pressure is inside. During inhalation, the pressure is coming from oxygen partial pressure of atmosphere is coming in. So that I write it down as a P sub out O2, which is coming outside to inside, so that's PATM. When it's an expiration, or then the flow comes outside from the inside, so that's alveolar volume flow rate, and that pressure, partial pressure of oxygen, because we are talking about mass balance of an oxygen, and that is coming from alveolar space. And during this, what else will involve in terms of the oxygen transport? In fact, when one cycle, we actually give this oxygen inside our blood, which is oxygen volume flow to the alveolar, through the alveolar wall. So I will define this as a through this as an oxygen flow like this. So then let's get back to the original mass balance equation, which is the accumulation, net accumulation over a period of time is influx minus outflux plus generation minus consumption. However, as we discussed at steady state, so steady state net accumulation goes to 0. And this generation and consumption inside this alveolar sac, there's nothing happening in terms of oxygen. So this part is also 0. And the assumption here is steady state. So then this equation now gets this way. So 0 equals, let's say inside. So this is a control surface, okay? So control surface, what's getting inside is an inhalation. So that is, we are talking about the oxygen, the amount of oxygen. So that's oxygen flow rate, volume flow rate, times oxygen's partial pressure. So that is volume flow rate of oxygen, which is coming from here, times partial pressure of oxygen, that is PO2 over P total pressure, and that's coming from outside, so we put ATM. So that's inside. And there are two components which goes outside, which is from exhalation to the atmosphere. So that's minus V alveolar volume flow rate and oxygen partial pressure over total, which is now it's from inside to outside. So that is supposed to be alveolar partial pressure of the oxygen. And there is a component which actually absorbs into the blood, which is shown here. And that part has to be considered, which is going out of the control volume. So minus volume flow rate of oxygen. So let me describe it a little more. So this is alveolar ventilation rate. And this is oxygen volume fraction. Oxygen volume fraction. So that means total volume of oxygen per unit time when we consider these two components. And this last term is about oxygen transfers from alveoli to the blood. So does it make sense? So now let's rearrange this equation, because what we are interested in is the relationship of alveolar partial pressure of oxygen and alveolar ventilation rate. So what we are interested in, the alveolar ventilation rate, which is this component, and then partial pressure of oxygen, which is especially in the alveolus, not atmosphere. So this one. Okay, so let's rearrange the equation 1 that now we are more interested. So we need a little bit of assumption, which is very much true, which is PT of atmospheric total pressure. It's almost the same as pressure of inside alveolus, which is not too different. So now we rearrange for this partial pressure of oxygen inside alveolus equals, you can rearrange this and what we will get is, it's a partial pressure of oxygen in atmosphere minus pressure of total pressure divided by alveolar ventilation rate times volume of flow rate of oxygen. So this here, what we are interested in is this alveolar partial pressure and the alveolar ventilation rate. So this equation is almost looks like y equals, let's say, a minus e over x shape, so that we can draw how this relation looks like. So simply we can draw this as this in x and y. So it looks like this. And it depends on if p value here is bigger, then it can move on to farther from the origin, from the x and y. So thank you for your attention. Now, let's continue that understanding how oxygen is carried by the blood and the quantitative relationships describing oxygen concentration. So for that, here, alveolar oxygen partial pressure versus alveolar ventilation rate, which I described a previous board exercise, and the relationship between alveolar ventilation rate and alveolar partial pressure oxygen will look like this shape. And here I put a table from the table 7.2, that relation of partial pressure of oxygen, CO2, nitrogen, and water. In venous blood, there's like this, and arterial blood, the oxygen partial pressure is 100 millimilli Hg, and alveolar gas has about 100, which is lower than dry air, and CO2 is 40 millimilli Hg, and there's a nitrogen, which is almost 79% of the air, like this. And alveolar gas is already saturated with water, so there's a 47 millimilli Hg of partial pressure of water. While in dry air, there's nothing here of water, but the others summed up about 760 millimilli Hg. And atmosphere is having a little bit of a moist. And expired air has the same saturated water partial pressure, while the O2 is about 120 millimilli Hg partial pressure. So the real question is about a person who sits with normal oxygen consumption rate. It's about 250 milliliter of oxygen per minute. While we know that a person suddenly stands up and then starts to run, then the oxygen consumption rate by the body is dramatically changing. It can be changing like 4 times, such as 1,000 milliliter of oxygen gas per minute. Can she do this without changing ventilation rate? So that is the question over here. Now let's consider, continue about this problem again. So here, this is the master equation connecting the alveolar ventilation rate and the partial pressure of oxygen in the alveolar space. So first of all, given the problem as a given oxygen consumption rate. So there's a 2 oxygen consumption rate were given, which is oxygen consumption rate, which is here. Let me show you here, like this. So this is a given. For example, for normal case, this is about 0.25 liter per minute, which is a normal state. However, when sudden exercise, this can become 1 liter, say, 1 liter per minute and during the sudden exercise. So as I talk about this equation 2 before, we can draw this again, that the x-axis is with respect to alveolar ventilation rate and y-axis as the alveolar partial pressure, PO2 ALV. Of course, the unit is millimilli Hg, and the upper limit is about 150 millimilli Hg. So the normal case, so this parameter depending on the B. So when it's small, it's closer to this point, supposedly kind of an origin that comes with, if you can see here, so that is a normal oxygen consumption. And we can see conventional conventional alveolar ventilation rate, let's assume it's about 12. So we have measured alveolar consumption ventilation as a 12. Let's say if it's 12, what happened here? So if it's 12, that is about 130 millimilli Hg. And when it becomes during the exercise, let's use blue. So during the exercise, and like this is a exercise curve. So oxygen consumption of this exercise, which is changing this parameter, which makes it farther from this point. And the question of, let's say about 5, alveolar ventilation of the 5, so from here, let's move on. Pause. Okay, sorry that I made a slight mistake here, so I will correct here. So this curve of normal ventilation is a little bit wrong, so I'm going to remove this and then redraw this. So that is like this. And the assumption of, let's assume the normal resting, we already discussed about alveolar ventilation rate, which is normal respiratory rate times alveolar volume exchange, which turns out to be about 5.3 liter per minute as alveolar ventilation rate. Remember, total ventilation from out of this, only those involved in actual gas exchange is an alveolar ventilation rate, which is not tidal volume, but tidal volume minus 150 milliliter times respiration rate. So which was about 5.3, then instead of this 12, let's say about 5, that actually gives about 130 millimilli Hg of partial pressure in alveolus. So it's an alveolar partial pressure of oxygen. Pressure of oxygen. So then suddenly we start to do exercise. What happens? The curve becomes this to this way because this oxygen oxygen flow, oxygen transferring from alveolus to the blood, the demand becomes this higher. So that means this, the same alveolar ventilation rate, it becomes to this point, which is very, very low as this is 0. So inside the alveolus, the partial pressure of oxygen precipitously decreased to almost 0, which is, of course, not great in that respect. So in that case, we cannot sustain this state because there's not enough oxygen partial pressure left in the alveolus. So during this exercise period, we can keep up this alveolar partial pressure, that we have to increase our alveolar ventilation rate. So otherwise we cannot sustain. So the answer for the question, what happens if a person sits with oxygen consumption rate of 250 milliliter of oxygen per minute and suddenly start to exercise, which required 1 liter of oxygen per minute, then she cannot keep up this and she have to change her ventilation rate, which is coming from 5.3 liter to much higher, to keep up with this oxygen consumption. So now let's move on. So we will discuss more about the oxygen carriage in the blood in next session.